Yeah, so I think we can start the class now. I hope my screen is visible to you and also my voice is audible.
Yes, sir.
Yes, sir.
Okay. So in the previous lecture, we had seen how to implement dynamic latches and also static latches. Right. So we saw that in the static latch, the data is stored in some loop, and in the dynamic latch, the data is stored on some, temporarily on some capacitor, right? And then we saw some styles of making these dynamic latches. For example, C square MOS latch we had seen. Okay, so which requires two non-overlapping clocks. Okay, for example here, just a second. Yeah. So for example, here, two non-overlapping clocks are required. That is clock and clock bar. So they have to be non-overlapping. So if they are overlapping, then the correct functionality cannot be obtained. Right. So it requires two non-overlapping clocks. So we had seen, and then we also saw this circuit, which was C square MOS, which is insensitive to clock overlap. Right. So it also has two clock requirement, that is clock and clock bar, but it is insensitive to clock overlap. Now let us talk about this pipelining. So in fact, this pipelining is very popular and very important technique by which the speed of the operations, or in fact in the data paths of microprocessors, you will find that all data paths of all microprocessors have this technique pipelining, so that the execution speeds can be increased. So how that can be increased? So let us understand by an example here. So let us say that I want to process two data, that is A and B. Okay. So now these two data are input to this register. They are saved in this register, and when the clock is high, this data will pass into this logic block element. So the job of this logic block element is to add these two data, right? And we want to perform an operation that is log of mod of A plus B. So this is what we want to do. Okay. So this circuit will do, that is output will be equal to log of mod of A plus B. So this is what this circuit is trying to perform, that is output here. So this is equal to log of mod of A plus B. So for this, I need to input two datas A and B. So initially they are stored in some register, and then when the clock is positive, that the positive edge of the clock comes in, the data enters this adder module, and then on the next clock it can enter this modulus module, and then logarithmic, and then finally the output comes out, right? So if somebody tries to find out the minimum propagation delay of this circuit, so one can say that minimum propagation delay can be found by using the same old equation, that is it depends on the setup time plus the clock to Q delay and plus the propagation delay of all these logics, that is logic number 1 here, 2 and 3, right? So imagine that, let us say that the propagation delay of all these three logics are same, right, which are given by TPD logic. Okay, so total propagation delay of logic will be obviously 3 times the logic delay of one logic. Okay. So if we try to find out the total clock required, that is clock edges required when the output will come out here. So in the first clock, this A plus B will be performed, right? So I'll write when the clock edge comes in, the first clock edge comes in, A plus B will be performed. Then in the second clock edge, modulus will be performed. And then in the third clock edge, right? So this is my clock here, for example. So this is, let's say, a positive edge triggered system. So whenever the clock becomes, makes a transition from low to high, so this is called positive edge. So when the clock edge becomes positive, that is at the first edge, this operation will be performed. Then on the second positive edge, that is here, that is modulus will be performed. Then on the third positive edge here, okay, my logarithmic will be performed. So that means I need at least 3 clock cycles to get the data output, right, out from this. Right? So minimum 3 clock cycles are required to get the data out. Okay? Now imagine you have a set of data, not just A, B, you have N A data and N B data. So you have a set of data that is A1, B1, A2, B2, A3, B3, yeah, and so on. Okay? So each set of data that is A1, B1, so that takes 3 clock cycles. So similarly, N set of data will say take 3N clock cycles. Okay? 3N clock cycle will be required for this circuit to produce the final data output. Okay. Now let us try to pipeline this circuit. So since we understand that by saying that if the circuit is pipelined, the execution speed can be improved. Okay. So let us say that we pipeline this circuit. So for pipelining this circuit, what we do is we simply insert registers in between the combinational logic block elements. That is, we include a register between adder and modulus. Similarly, a register between modulus and log operator, and then finally one more register which is already here at the output to store the data, that is the output values, right? So just simply we have included 2 registers, that is register number 1, this one, and this one, in between the combinational logic element, and we say that my circuit is now pipelined, and now the same operation can be done at high speed. So high speed performance can be obtained now. So how it is high speed? So let us try to understand. So let us say that in the first clock cycle, when the clock cycle is first clock cycle comes in, so A1 plus B1 is performed. Okay. Now in the second clock cycle, this A1 plus B1, so that will be shifted. A1 plus B1 will be shifted to this modulus operator or modulus block, modulus combination logic block. So now in the second clock cycle, mod of A1 plus B1 will be performed. Okay. And in the same second cycle, next data, that is A2 and B2, will be put in here. So second clock cycle, A2 plus B2 will also be performed. Right. So this is in the first clock cycle. Okay. So this happens in the second clock cycle, and this also happens in the second clock cycle. It is A2 plus B2. So that is also being taken. Now in the third clock cycle, so obviously we'll perform log of mod of A1 plus B1. Log of mod of A1 plus B1 can be performed in the third clock cycle. And in the third clock cycle itself, you will see that the output is available. Yeah, first set of data is completed. Okay. Now in the third clock cycle, so here you will also perform mod of A2 plus B2. Okay. And in the third clock cycle, in the first block, so which was sitting idle, so we'll again perform here in the third clock cycle, we'll perform A3 plus B3. Okay. And so on. Right. Similarly, in the fourth clock cycle, the next data set will be here. That is, in the fourth clock cycle, you have A4 plus B4 being performed by this element. Okay. And in the fourth clock cycle, this will perform mod of A3 plus B3. Okay. Similarly, in the fourth clock cycle, you will have here you will have log of mod of A2 plus B2. Mod of A2 plus B2. So that means this pipelining, what it is doing is that it is not letting any of these elements sit idle. Okay. So earlier we had seen that this was taking complete 3 cycles, and in the rest of the cycle, that is in the third clock cycle, the output was coming, and in the second clock cycle and the first clock cycle, right? So I mean in the third clock cycle, these two were sitting idle. Okay. So now this pipelining is not letting the other elements sit idle. Okay. So this is also working, that is addition is also working in the same clock cycle, modulus is also working, and log is also working, right? So that can be again, I mean the same thing has been explained over here. That is, in the first clock cycle, the adder is working. Second clock cycle, both adder and absolute value, that is modulus, is working over here. Then in the third clock cycle, all 3 are working, and you have first set of data is already available. Okay. Second set of data is also available here in the fourth clock cycle, and in the fifth clock cycle you have third set of data also available, complete operation on third set of data, so that is also available. So if we would have done the same thing on a non-pipeline system, that is log of mod of A3 plus B3, that would have been available after 9 clock cycles. right? So after 9 clock cycles, log of mod of A3 plus B3 would have been available if you have a non-pipeline system. But here you will get log of mod of A3 plus B3 after just 5 clock cycles. Okay. Similarly, let us say we have 30 sets of data, right? So A1 to A30 and B1 to B30. So the total time taken by pipeline system will be 32 clock cycles. 32 clock cycle to process 30 individual set of data. Okay. However, the non-pipeline system, so that would have taken how much? 90 clock cycles for processing 30 data. Okay. So that means the total, minimum clock frequency. If we say that, let us say clock to Q and to T to set up, so they are, let us say, very small in comparison to the propagation delay of logic. So one can say that the minimum frequency, clock frequency or minimum clock period, so that becomes equal to minimum clock period divided by 3, right? So that is, for a pipeline system, the total clock period required is 3 times smaller than, or 1/3 of the clock period required for a non-pipeline system. So that means this system is faster, pipeline system. So that's how the pipeline.
So can you repeat that 32, how it comes 32?
Yeah, so 3 sets of data, not 3 set, 1 set takes 3 clock cycles, right? Then 2 sets of the data take 4 clock cycle. Similarly, 3 sets of data take 5 clock cycles. So similarly, 30, I mean, just you have to just add 2 more clock cycles for the final data to come out. So 30 sets of data will take 32 clock cycles to produce the data. That is log of mod of A32 plus B32. Sorry, A30 plus B30. So that will be available after 32 clock cycles. 32 clock cycles in a pipeline system. But however, in a non-pipeline system, each set of data takes 3 clock cycles. So 30 clock cycle, 30 set of data will take 30 multiplied by 3 clock cycles. That is 90 clock cycles. Right? So that means this is more faster system. That is, pipeline system can be more faster. In fact, the clock period can be 1/3 of the clock period required for a non-pipeline system. So that is how one can say. So in fact, you will find that this term, that is resource utilization. So the resources are completely utilized in the pipeline system. So this is the main objective. That is, you don't want to sit any of the resource sit idle. So all these are resources, all these combinational logic blocks. So earlier we had seen that when clock cycle 3, in clock cycle 3 here, resource number 2 and 1, so both were sitting idle. Okay. But here, when you make a system pipeline, all the resources, that is all these combinational logic blocks, are used in every clock cycle. So they are not allowed to sit idle. Right? So this is more important thing here to notice, that is, because of the resource utilization, 100% resource utilization, the system speed can be, or system performance can be increased. So this is very popular in microprocessors, especially in the data parts of the microprocessors. Now let us also talk about another dynamic latch, another dynamic latch. Let us talk about. Then we'll try to make a resistor. So let us talk about another dynamic latch, which is called TSPC. That is true single phase clock, based latch. Yeah, true single phase clock. Yeah, so here, obviously, single phase clock means you don't have a clock bar appearing over here. So same, one phase of clock, that is clock only is present here. No clock bar is present over here. So that is how I say it's a single phase clock system. Okay. So this is a positive latch. Okay. So here you will see that this positive latch is transparent when clock is 1. So when clock is 1, so whatever data is supplied here, so that data comes here, it becomes D bar. Okay. And then this D bar again passes through this inverter. I mean, these are 2 CMOS inverters. So both are active when clock is 1. So D bar, so if you apply input, so complement of input comes here, and in the same phase, again the input comes here. So that is, output is equal to input when clock is 1. So, or we say that this is a positive latch. Similarly, a negative latch can be implemented, which is transparent when clock is 0. So when clock is 0 over here, so this PMOS transistor is on. Okay. So whatever you supply here, so complement of that comes over here, and then finally again the complement of this comes over here. So this becomes equal to input. So output is equal to input again. So this is a negative latch because it is transparent when clock is 0. That is, output is equal to input when clock is 0. Now, one can also think of including logic in this two single phase clock based latches. Okay. So for example, one can replace these PMOS and NMOS by pull-up networks and pull-down network, right? So pull-up network and pull-down network. So for example, a AND latch using TSPC logic is implemented over here. Okay. So for an AND gate, obviously we need two NMOS in parallel here, sorry, series here, and similarly two PMOSs in parallel. So this represents an AND gate, that is when clock is 1, so this latch is transparent, that is you get a AND over here. So NAND over here and AND over here. Right? AND operation. At the Q you get a AND operation. Now based on this true single phase clocked latch, you can also think of making a register. Right? So how this register is implemented? So for implementing a register again, you have these two, in fact 3 CMOS inverters are here now. This is one inverter, then this is second one, and this is third one, and then the last one, this is fourth one. So this is to invert the output. Yeah? So let us say that we have 3 inverters, 1, 2 and 3. Okay. So by which we make a true single phase clock register. How this works? Let us say when clock is 0. Okay. So when clock is 0, this is on. Right? So when clock is 0, this is on, and this one is off. Oh, this is also on. Clock is 0, so this is also on, but this is off. Right? And this is also off. Right? So when clock is 0, this situation exists. That is, this transistor is on, this is also on, and this is off, and also this is off. Right? So whatever D you apply, the complement of that appears over here, right? Because this is on and this is off, right? M1 is off here, I'll write off. So whatever you apply, the complement of that comes over here at node number X, right? And at the same time, since this MOSFET is off, so this inverter, this is in pre-charge phase. That is this node Y, so that will be charged to full VDD. So when clock is 0, that is this inverter is on. Okay. So at X I have D bar, and at Y I have VDD. And this inverter, that is this entire pair total, so this is in hold state. Okay. Because this transistor is off and MOS is off. Okay. So this is in hold state, yeah, so this is VDD, so this is also off. So this is in hold state, that is whatever data was stored here, since it's a dynamic latch. So whatever data is stored here, or maybe here at this point, whatever point you want, you can consider. So either of the 2 points. So that data will remain here. And of course, this capacitor needs refreshing at regular rates, right? So this is in hold state. This inverter or this entire pair is in hold state. So whatever data it was retaining earlier, it will retain the same data. Okay. Now let us say clock is changed to 1. Okay. So clock becomes 1 now. Okay. So clock becomes 1 here. So obviously that means now my this transistor which was on, so this will become off, this will become on. Okay. So this will become on. Okay. And imagine if I had a 1 over here, so this is also on. So that means this circuit, so this is in evaluation mode, right? That is this VD, node Y, which was earlier held at VDD, now this will lose its charge and it will become 0. Okay. Now this 0 is applied to this PMOS, so this PMOS also turns on. Okay. And since clock is 1, so this also turns on, right? And this is off. This one is off. Okay. So whatever data this becomes 0. So obviously that means this data which was held at X in the previous clock cycle, that is when clock was 0. Okay. So this is transferred to this node Y when clock is 1. So clock is 1, these two transistors are on. So obviously if I have, let us say, D bar here appearing here, because I had applied first D here in the first clock cycle, so D bar was appearing here. So now D appears here. So then again here D bar appears. So that is why Q bar is written over here, and then which is again inverted here. So we get D here. So this is how the operation of this could be estimated. So when clock is 1, that is, it is a positive edge triggered resistor. So whenever the clock makes a transition from low to high, that is 0 to 1, the D input is copied to the Q output here, right? So D is copied here. So that way, in fact, the operation of any logic circuit can be understood. Okay. So this was all about, I think, the sequential part. Combinational we had discussed. So sequential part is almost also complete. So I'm done with the this portion of the syllabus. Now let us come on to the other portion of the syllabus, which is very important and which is called timing issues. I hope my screen is visible to you. The slides are visible. Yeah, is it so? The slide is visible to you? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, okay. So let us now talk about the timing issues. So this is, as I said, the most important part of this course, right? In fact, all the companies which will, maybe take your interviews for, job positions, they are very much interested in this part, right? That is the timing issue. So this is very important. Okay? Please pay attention, especially to this part, and try to understand this thoroughly, right? Timing issues. Okay. Yeah. So let us talk about the timing issues. So obviously, timing in a digital circuit or any circuit, the timing is most crucial or most important, because if there is a mismatch in timing, so that obviously means that the entire circuit operation is almost malfunction, and whatever circuit or whatever chip you have created out, so that may turn into a waste circuit or a waste chip if there are timing mismatches, because of these timing mismatches the circuit may not behave as desired. So you have made a circuit for, let us say, some logic. Let's say you have tried to make something, right? Maybe a multiplexer, or maybe anything, maybe a full adder or something, or maybe even complex circuit. So obviously, and also if it is a sequential circuit, so sequential circuit, they depend largely on the timing. So the timing should match. I mean, the data should be available at, the very instant of the time at which it is desired. If the data appears at a later time, then it is of no use. And maybe in fact, because of the arrival of data which is happening late arrival of data, the circuit operation may change. Okay, so that is why this timing is very important. And in a synchronous circuit, this timing obviously comes from the arrival of the clock signal, right? So we say that in a synchronous system, the entire circuit operation is synchronized or controlled by a common single global clock, right? So there is one single common global clock in a synchronous circuit, which will synchronize all events in the circuit or on chip, right? So for example, let us say that there are two registers in this circuit, and we want that this clock, this should arrive at the same instant, right? That is, let us say that my clock, let me draw, and let us say this is a positive edge triggered resistor. Both are positive edge triggered resistor. So in this sequential circuit, I will want that at the first positive edge. So this is first positive edge, and this is second positive edge. So at the first positive edge, I want my data input to be sampled by this resistor. That is at the first clock edge. That is when clock makes a transition here, first clock edge. I want this data input So that should be latched into this register 1. Okay. And then during this part of the clock, I want the data to traverse through this combinational logic block, and this combinational logic block should also process completely data, and the processed data should be available at the input of register 2 at the second edge. Okay, that is, at the second edge I want the processed data to be sampled by this register. That is, at the second edge, after sampling the data should be available here at the output. Okay. So the data is input to this register at the first edge, and data is out from this register to at the second edge. In a synchronous circuit, I would like that the circuit should behave like this. Now, because of the clock mismatches, maybe it is possible that this edge arrives late, second edge arrives maybe here. Second edge, maybe it arrives here, or maybe second edge also, it can arrive early also. Here maybe it arrives. Then there is a problem. If it arrives early, okay, and the combinational logic block has not finished processing the data is not available, the data is available at this point. Okay. So whatever data at that moment is available, that is, this combinational logic will obviously produce continuously, it will keep on producing data, but the final value is not available until this point, okay, which is actually the propagation delay of this combinational logic, right? So before that, some data is obviously available at this point. Now register 2 will obviously then process this data, that is, which is available at this point, right? So which is some garbage value. So obviously garbage output will come out, right? So which is not of any use, right? So this is a problem because of timing mismatches, or what we call as clock skew, or the delays which are introduced by clock. So this is an example of positive clock skew, not positive, negative clock skew, because the rising edge of clock 2 is appearing earlier than the expected time, right? So this is how the clock is important, right? That is, the arrival of clock at regular interval is important. Now, why these clock uncertainties can come? So obviously you will find that if suppose my clock source is here at this point, so obviously this point, that is register 1, so this is near to clock source compared to register 2, right? So I have this much length, extra length. I mean, this is close to clock, register 1, register 2 is far from clock, so total distance it has to cover, the clock has to cover, is this much. So that means this clock has to be obviously connected by some interconnect wire to register 2. So that interconnect wire obviously will have some RC delay. So the delay from here to here, and the delay from here to here, so this is different, right? So that is, this clock uncertainties or clock skews are a result of delay mismatches between the clock source and clock destinations. Okay, so one has to, designer has to overcome these issues, maybe by some methods, for example by some clock routing techniques, for example S3 clock distribution techniques, or many more are there. So that's how the designer has to equalize the delay from the source to the destinations. Okay? Otherwise, this kind of situation can appear, and the entire circuit operation will be disturbed, and the circuit will result into a waste circuit. Right? Now, these clock uncertainties, right? That is, when we say clock uncertainties, so obviously we mean clock skew, and also the other common clock uncertainty is clock jitter, right? Now the sources of clock skew and jitter, if we talk about, so what they could be. So first source could be the clock generator itself, right? So today we see that every chip has its own clock generator, not just one clock generator. There are maybe 4 or 5 clock generation schemes present, that is 4 or 5 clocks are present in the system, so each have a different clock generator. So this clock generation scheme which is present on chip, or clock generator, can also result into clock uncertainties, because these clock generation scheme, so they involve, the common component of generating any clock would be a VCO, that is voltage controlled oscillator. So this is a common element which is required in any clock generation scheme. You will require a VCO, that is voltage controlled oscillator, and this is an analog component, this VCO, right? and this VCO, that is analog component. So this is very much insensitive to the device size variations also, and the power supply variations also, right? That is, it varies very much on the W by L ratio of the devices, and also on the power supply variations. So if there are any variations in the power supply, or there are variations because of process variations, the device in this VCO, that is device which are used to implement this VCO, so they may also be different in size. Okay, so because of the process variations, this VCO can easily pick, the performance will be different, right, because of the process variation, and also because of power supply variations. This can also disturb the operation of this VCO. Right? So then this can also result into jitters, clock jitters. So those are possible. So before, in fact, talking about these other sources, let us talk about this clock skew and jitter briefly.
Sir,
Yeah,
sir,
please.
these jitters will come into picture with the length, or it can be come into picture with the speed of that signal also.
So both are possible, right? So jitter are basically temporary variations. So they can be coming from, maybe because there are some uncertainties with the clock generation scheme, or maybe there are some temperature variations on chip, or maybe because of some noises which are big, right? Random noises. So jitter can happen. So what is jitter? Let us first understand. Okay? So before that, let us talk about clock skew. So clock skew, if I say skew, so skew means spatial variation in temporarily equivalent clock edges. And these can be either fully deterministic or maybe random also, right? So clock skew is spatial variation in the clock signal. Okay? And clock jitter is the temporal variations in the clock signals. Okay? So So what is clock skew? Let us understand by this picture. So clock skew is spatial variation, right? That is, let us say my clock edge, it starts at this point, okay, the original clock edge, and it ends over here. Okay, so this is my one clock period. Now, because of clock skew, there will be spatial variation in the clock. Okay, so here spatial variation in the clock. That is, my clock may start from at this point, and it can also end at this point. Okay, this is spatial variation. Or maybe it starts at this point and it ends early. Right? It starts late and it ends early. Or maybe it starts late at this point, okay, and it ends also late at this point. Or maybe it starts early, and it ends late. Right?
Sir, excuse me, sir.
Yeah, please.
Hello.
Yeah, please say.
Sir, means the time period will be same, sir, here.
No, time period can also be different. So that is what
Oh.
I'm showing over here, right? So these two time periods are different.
Okay, sir.
These two time periods are different, right? So it could be either starting late, that is this point here. This is starting late, okay? So it is starting late, and it is ending early here. So in this case, time period is same, no issue. Okay? Let us say if this is delta and this is also delta. So in this case, the time period is okay, same. Okay, but let us say it starts late, okay, and it no, in this case, that is, it starts late and ends also late. So in that case, we have same clock period. But if it starts late and ends early, that is at this point, so then the clock period is different. That is, let us say that this is T double dash, and if this was T dash. T dash. So T double dash is smaller than T dash. Okay. So there could be spatial variations in the clock signal. That is, clock may start early and end up either early or late, or maybe it starts late and end up either early or late. Right. So that is called actually clock skew. Okay. Now, if we talk about clock jitter, so I'll go back here. So jitter is temporal variations in the clock signal, right? So temporal variations would mean here, let us say that the strong line, that is the solid line, that is from here to here. So this is my original clock, the solid line. Okay. And because of these temporal variations, the starting and even ending, so they may fluctuate for a temporary moment. Maybe the actual clock is this much t. So for some time, maybe for some time instant, you will see that the clock starts late here, okay, and maybe it ends also late. So this is temporal variations, not constant. Okay. So it changes with time, or what we call as fluctuations in the clock signal. It may appear that clock is starting here late at some instant of time, and then at other instant of time you will see that the clock is starting here itself, or maybe at other instant you will see that the clock has started early. So some sort of temporal fluctuations or variations, or what we call as vibrations in the clock signal, right? So these are called clock jitter. These are not permanent, these are temporal fluctuations or variations in the clock signal. Okay. Now let us come on to the sources of these clock uncertainties, that is clock skew and jitter. So clock skew, one source we discussed, that is clock generator or clock generation scheme itself may impose the uncertainty, that is jitter can be possible because this voltage control oscillator, which is a part of this clock generator, so that is an analog component, and it is very much insensitive to the device sizes and also the power supply. Okay, now the next source of uncertainty, so that would be when you are driving the clock signal, okay, and if the length of the from source to destination, so that is large, so you will try to include buffers in between, as we had seen that interconnects can be also driven by buffers. Okay, now the delay of these buffers, okay, so if it is same, then there is no problem, but if there are different, right, you have though designed by considering that the delay of these buffers are same, okay, but because of the process variations, again because of the sizes of PMOS and NMOS which are used to implement these buffers, so they may not be same. So because of that, the delay of these two buffers, these three buffers may also not be same. Okay, then that means that the overall delay with which you had estimated, so that may be different in the final IC. Okay, the fabricated IC may have a different final delay because of the process variations, and because of those process variations, the delay of these buffers was different. Okay, so that delay, the mismatch in delay causes the mismatch in the delay of this wire, right? And if there is a mismatch in delay, so obviously that means the clock cannot be routed at the same point to different destinations, right? So that means again I have a situation of clock skew. Then the third uncertainty would be because of the interconnect parasitics, especially when we talk about multi-layer system, that is multi-layer interconnects. So we understand that in the each layer, that is let's say we have 3 layers or maybe 4 layers of interconnect. So each layer is separated by a dielectric, right? Now because of these process variations, again you will see that the thickness of this dielectric, so that may also differ. Okay. Now if the thickness of this dielectric differ, then the capacitance associated with these wires, so that may also be different. Yeah? Because if you consider the parallel plate capacitance model, right, so which includes that, which says that you have a wire over some semiconductor and which is separated by a dielectric. So the capacitance depends upon the thickness of the dielectric, and if the dielectric thickness is different in these layers, so obviously the capacitances will also be different. So RC delays will also be different. Okay, so that means there would be a mismatch in delays because of these interconnects, again because of these process variations, that is the dielectric width or thickness are not same. Okay, so again that means that is a source of clock skew or clock delay. Okay. Now the other source would be the power supply, right? So because of variations in power supply or some noises in the power supply, again you will see some jitter, or maybe the clock power supply has some huge variations, fluctuations, so that can actually affect my clock signal. Okay. So again, you may have temporal variations also possible and spatial variations also possible in the clock signal because of power supply variations and also the noises in the power supply. Then the other important parameter which decides the clock uncertainties, because of which clock uncertainties could be present. So that is actually temperature, right? So temperature can also create this clock uncertainties. So how? You remember that the mobility, so that depends on temperature, and also the threshold voltage of the device depends on temperature. Okay? And we also understand that in a clock gating system, that is, I think we haven't talked about this clock gating. So let me tell you that clock gating means that in the portions of the chip where you don't want the clock to be connected. Maybe let us say that this portion 2 of my chip is idle, so I don't want to route the clocks to portion 2 of the chip, right? So what will I do is I will gate the clock, that is I will cut the supply of clock in this portion of the chip, right? So that is called clock gating technique. So that will actually save the clock power dissipation because the clock is not required in portion number 2 of the chip. So clock should not be supplied. So clock supply is cut, so which is called clock gating. Okay? So the idea is to save the clock power dissipation by this clock gating technique. Right? Now, because of this clock gating, you will find that the temperature of these two portions on the chip, that is 1 and 2, so they will be different. Right? So obviously, if this is not active, portion number 2 is not active because clock is not supplied to this portion. So obviously, this will be more cooler than portion number 1, which is very active and where we have supplied clock. Right? So because of clock gating, the temperatures within the same chip, right? So that may differ. Okay? So this portion may have a different temperature than this temperature. So obviously, the devices in this portion, okay, and this portion, okay, so they will have different threshold voltages because threshold voltage depends on the temperature. Vt, that is Vt of a device, so that depends upon the temperature, and also the mobility, that is electron mobility of a device, so that also depends on temperature. So here in the two cases, that is portion number 1 and 2, since they both are at different temperatures, so Vt and the mobility of the devices in these two regions will also be different. So that obviously means performance, that is delay of these devices, will also be different. Okay? And these devices are actually used to implement these buffers also. So obviously the delay of the interconnect which is carrying the clock signal, that will also be different. Right? So this is also a very fine source of the clock uncertainties, that is clock skew, may be present because of the temperature variations, okay, on chip. Now next is because of the capacitive loads and also because of the coupling to adjacent lines. Okay. So it is possible that the same clock signal has a different load, right? So signal is same, clock signal is same, but the clock loads are different. So obviously when clock loads are different, the clock line, that is line which is feeding clock, so that will have a different delay because of the extra capacitive load which is present on the clock. Right? So two different clock lines which were assumed to have same delay, they may have different delays because of different capacitive loads at the output. Okay? So because of that also you will see clock uncertainty, that is skew will be there. Then coupling to adjacent lines. We understand we have very dense layout today, so the interconnect lines are also very closely spaced. So obviously there are possibility of mutual capacitances existing between the two lines on the same layer. Okay? So obviously that means the crosstalk, or what we call as noise between the two lines, are possible. So because of the crosstalk between two lines, or because of mutual capacitance here, right, between these two lines, so it is possible that any change on this signal on this line can affect the signal change on this line, right? So that means again it is a source of uncertainty in the clock signal, that is skew and jitter, both are possible. Okay? So these are all the actually the sources of clock uncertainties in the chip, right? Then there are many more, okay? But yes, these are some of the basic sources of clock uncertainties. Now let us talk about this positive and negative skew in somewhat more detail. You will notice that in a circuit, positive skew will always exist when both the data and the clock, right? So both the data and the clock, they are moving in the same direction, right? So for example, here in this circuit, we see that the data, that is this input data, so this is moving across this chain through register combinational logic, that is left to right data is moving, okay? So this is my data, and clock, this clock, so this is also moving from left to right. Okay. Now in this scenario where the data and clock both are moving in the same direction, the positive skew results, right, in this scenario. Okay. And in the other scenario, that is this case, you will see that is the negative skew. You will find the data and the clock both are moving in different directions. Data is moving in the same direction, but clock is now moving from right to left, right? So this is my clock moving from right to left, and data is moving of course from left to right. So in this scenario, always you will see that negative skew can be produced, right? That is, data is moving from left to right and the clock is moving from right to left. Data and clock both are moving in the opposite directions, negative skew will result. Data and clock are moving in the same direction, positive skew will result. Okay. Now let us consider this example where positive skew results because of the data and the clock both are moving in the same direction, right? So data and clock both are moving in the same direction. Let us say that a positive skew exists over here. So positive skew here means, in fact, let us try to understand first of all the operation of this circuit, how this circuit operates. So again, it operates in the same way, that is, in the first, this is a positive edge triggered system. So that means at the first edge of the clock, maybe this is my clock. So at the first edge of the clock here, this is first edge, and maybe this is the second edge. So at the first edge of the clock, positive edge, the data will be sampled by this resistor 1, and it will be available at this point, that is processed by this combinational logic, and is available before clock edge 2, because at clock edge 2, positive edge, the same data will be sampled by this resistor 2, right? So this is how this sequential circuit will operate. Okay. Now let us say that I have a clock skew in this circuit. Okay. So clock skew means I have a positive skew, that is, this is called launching edge. Let us say this one edge, right? So this is clock 1. Let us say that resistor 1 receives clock 1. So this is clock 1, let us say, and resistor 2 receives clock 2. Okay, clock is same, but because of the delays in the clock, or because of the differences in the arrival time of the clock, I say that this is clock 1 now and this is clock 2. So now clock 2 arrives late, okay, than clock 1. So by delta time, by this much time, clock 2 arrives late. That is, the positive edge of the clock arrives late by delta at resistor number 2. Okay, so I have now drawn two clocks over here. Okay, so I say that this is my launching edge, that is edge number 1. So launching edge here means that the data is launched into this resistor at this edge. Okay, and this is my receiving edge 4, that is, at this edge the data is now received or launched into register number 2. Okay, so earlier, if there was no skew, the data would have data would have been received by register 2 at this point itself, edge number 3. But because now there is a delay in arrival of the clock at register number 2, and that delay is delta, let us say, right? So the data is now sampled by register 2 at edge number 4. Okay. Now let us say that the earlier the total clock period, so that was T clock, right, from 1 to 3, it was T clock. Now because of this positive skew, so this total clock period, that is after this much time only this data will be present here at the output. So this data is present now here at the output after this much time, that is t clock plus delta, right? So after t clock plus delta time, the data is processed by register number 2. Okay, so if somebody asks me to find out the minimum clock period required for this circuit to operate correctly, okay, so I'll utilize the same concept which we had seen in the previous lecture. That is, I would say that minimum clock period now is t clock plus delta, so that should be greater than or equal to clock to Q delay plus the delay of this logic, combinational logic, plus the setup time, right? That is, after this time, my data should be available at, the data would be processed, right? So I need at least this much time. That is, after this much time, the data will be present here at this point for processing by register number 2. So maximum or minimum clock period required for this circuit to operate correctly is now this. If there was no skew, so I would have said that the minimum or maximum clock period is t is greater than equal to t clock to Q plus propagation delay of combinational logic plus the setup time. Okay, so if we bring down this delta towards the right hand side, so now this minimum clock period changes. So now I need a minimum clock period which is now equal to this much minus delta. Okay, so earlier if there was no clock skew, so then this was only this much, that is t clock to Q plus t logic plus t setup. But now if I have a positive clock skew, so now my clock period has improved. So that means I need a smaller time to process the data. Yeah, it seems that apparently that this is actually improving the performance of this circuit. That is, the operation of this entire processing of data that can be now done in a smaller time, right? So earlier the clock period required was this much, t setup plus t logic plus t clock to Q, but because of clock skew, it seems that minimum clock period required for this circuit to operate correctly, this reduces with increasing clock skew. So one would argue that why not increase this clock skew? So since it is beneficial, my circuit is becoming faster. Okay? So this looks correct, but then it will, this skew. So this will also create race conditions. Okay, that is, you will see that this combinational logic. So this has to present data. At edge number 4, the data should be present. But now imagine if the delay of this combinational logic plus the delay of this is very small, okay, smaller than delta. So let us assume that the delay of the combinational logic plus the delay of this flip-flop, this is smaller than delta. So then what happens is that the data to this register 2 that may be available at this point even. So that means the register 2 can process the data as edge number 2 also. So at edge number 2 also it can process the data, and it can process the data at 4 also. So that means some sort of race condition exists here in this case. So one cannot increase this delta by a certain amount, okay, though this looks beneficial, but actually it is harmful, right? Because now the race conditions will exist. That is, this data at this point would be written at this edge also, second edge also, and fourth edge also, right? Now similarly, let us now talk about the negative skew. Okay. So negative skew here means this clock edge 2 here, right? So this arrives early, even earlier than clock 1 comes in over here, right? Or maybe what we say is that clock edge 4 here, we want to sample the data by R2 at clock edge 4. So clock edge 4 arrives earlier than clock edge number 3. not, yeah, this is 3. Or maybe clock edge 2, this arrives early or earlier than clock edge number 1. That is, the receiving edge arrives before the launching edge. Okay. So in this case, you will see that this is a case of negative skew. Okay, that is, this is skew delta. So this is delta is negative, that is less than 0. Earlier in the previous case, delta was, that is this much, which was greater than 0, positive skew. Okay, negative skew means delta is negative, that is less than 0. Okay, right. So delta is less than 0. Okay, so this is the case of negative skew. Okay. Now let us again come back to this positive skew. Okay. So we discussed in the positive skew that if the delay of this combinational logic plus the delay of this register is smaller than delta, okay, then the data may be available to be processed even at this point, or maybe even at the edge number 2. So this will result into a race condition. Okay, so that means this puts actually a condition for holding the data for certain time, that is hold time condition is existing here. So we don't want the data to be written at 2 by register number 2. We want the data to be processed only at edge number 4. So that means I would want to hold the data constant for a certain amount, right? So what is that certain amount? So that is the propagation delay or the contamination delay or the minimum delay of this combinational logic block plus the contamination delay or minimum delay of this register. So that should be greater than delta, that is skew, plus some hold time, right? So that is, we want the data to be available after the edge number 2. That is, edge number 2 is appearing here at this point. So we want the data to be available for processing by register 2 after edge number 2. Otherwise, race condition will exist. Okay. So to make that happen, I want the delay of this combinational logic plus this register. So that delay has to be greater than this delta plus some hold time. That is this condition. So this condition has to be fulfilled. Okay. Or maybe if I bring this t hold on the right hand side, so this condition further changes. That is, my delta, that is skew, should be less than, or maybe, yeah, so skew should be less than, or maybe clock to Q delay of the register plus the contamination delay of logic minus hold time should be greater than the skew, right? So this is the condition which must be true, not for this circuit, but for any circuit. Okay, so otherwise the data will be processed at edge number 2 instead of edge number 4. 4 also it will be processed, 2 also it will be processed, which we don't want. That is called race condition here. Now let us come on to negative skew. Negative skew case here, where delta is negative. So delta is negative here. So if I put delta negative here in this equation, delta negative in this equation, if I put delta negative here in this equation, so that means this condition is already true for a negative skew system. That is, the propagation delay of combinational logic plus propagation delay of register 1. So that is greater than this quantity, delta plus t hold, because delta is negative here, not positive, right? So that means, that would mean, okay, so here if I put delta as negative, so I see that is skew is negative. So I see that this equation, this is always true. The same equation, this is also 10.4 of your textbook, and this is also 10.4. So in a negative skew case, you will see that this equation, that is this condition, is always true. So that would also mean that this circuit will never fail. That is, circuit which has negative skew, so that will never fail, because this condition is automatically true. So that means the system will never fail, okay? Because this condition is satisfied, because delta is less than 0. Skew is less than 0. Skew is negative here. But yes, this negative skew directly impacts the performance of the sequential system. Performance of the sequential system will obviously be affected, but this circuit will never fail. Now, in an actual scenario, right? Somebody who is designing a digital circuit. So
Sir,
in an actual scenario, okay, maybe okay, let us stop here itself. So we'll talk about this later. Yeah. So if you have any question, then maybe you can put on your queries.
Hello, sir.
Yeah, please.
Sir, can you please go to the slide, the last one, the previous chapter, last one picture you showed? The three inverters are connected there.
Okay. This one?
Yes, sir.
Okay.
In this case, when the clock is 0 and D is 1.
Just a second. Let us not say D1, let us say D itself. And then one
D is
can
1.
assume D as 1 or 0. Let us say D itself. So D bar comes here.
No, sir, I want to ask if D is 1, then M5 is connected with M1. So M5 and M6 are ratioed or not in this case? If they are not ratioed, then both are tried to write on Y.
Just a second. Can you repeat? D is 1?
D is 1 and clock is 0.
And clock is 0.
Yes,
Okay.
sir.
So clock is 0. Okay. So here 0 comes in. Okay. Then
X is directly connected through the M1 to the ground.
X is connected directly, yeah, M1 to the ground. So that is why it is 0.
Yes, sir.
Correct. Then
And in that case, okay, Y is 0. Okay, sir. Sorry, I got some
it will
confusion.
always create confusions. So just sit, relax, sit and relax, and then write everything on paper. Then you will understand, because it will always create confusion. Even when I try to relook the same thing other times, so I also get confused many times. Yeah. So better to write everything on paper and then try to find out the outputs. Yeah.
Okay, sorry, sir. I got
Yeah.
confused.
Yeah. Anything else?
Sir, why the name the true single phase?
True single phase, because we have only just one clock. We don't have clock and clock bar, that is two different phases of clock, right? So here in the previous case, where we had two clocks, that is two phases of clock, the clock and clock bar. So they are out of phases, right? Two phase. So there we have only clock. So there are not two phases of clocks, only single phase of clock. So that is why it is called single phase clock, true single phase clock. Yeah, anything else?
Sir, in practical situations, so the adjacent periods of the clock, sir, can they increases or decreases in practical situations?
Can you repeat in practical situation?
So in practical situations, the adjacent periods of the clocks, positive one, negative one, so will they start increasing or decreasing in practical situations?
Yeah, they can, obviously. In practical situation, when the circuit comes up, you have a fabricated copy of the circuit. Yeah, so when the fabricated version of the circuit comes, so these things can happen because of process variations. We had seen that because of process variations, the skew and jitter both can exist. So they can exist, right? So yes, of course, there are ways to overcome them. So that ways we'll talk about those ways very soon.
Okay, sir, thank you.
Yeah. Yeah. Anything else?
Hello, sir.
Yeah, please, please.
Unlike Q, is the jitter is confined to one single pulse only, since it is temporary?
No. So it can vary because of many reasons. Many sources of jitter can be there, and the clock durations can also vary at every instant of time.
Means
because
means sometimes jitter and skew they are similar. It's going like that.
yeah, for some instant of time, maybe, because jitter are temporal variations, right? So they may not be present at the other instant. At some instant it would be present, then the other instant it may not be, or it may be something different. So that means, the clock is some sort of, vibrations are going on in the clock. Vibrations. Clock is vibrating.
Okay, sir.
Yeah. Anything else? So if you have, nothing to ask, then let us end the class here itself, and we'll meet on Tuesday then. And in the mid-sem 2, we'll try to keep things that have been covered till today. Okay. Yeah. So let us meet on Tuesday now. Okay.